Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am a teacher and one of the co-founders here, along with my younger brother, AJ Raj. As you can see, we have a new Algebra 2 lesson, and it's going to be a part 2, a continuation to the lesson we started in the last video called Polynomial Functions. We're going to be looking at functions that have exponents that are higher than 2. So we're going to be looking at polynomial functions that come after quadratics, including cubic functions, quartic functions, quintic functions, etc. in this unit. And this is just the first lesson. So in this video in particular, we're going to be looking at several practice problems. There's 6 to be exact, and one of them I'll be showing you 2 different ways to solve it. And in these problems, we'll be doing things like classifying polynomials, describing end behavior without graphing, and then being able to graph the polynomial, also describing end behavior using tables, and then we'll have a challenge problem. And I'll incorporate the TI with the graphing as much as I can in this video. Before we get into it, I would just want to do 2 things. I wanted to show you the funny joke I had up on the slide. There's an eel. That's an eel, and it's found in the ocean. And the eel is pretty much saying what happened when the quadratic polynomial fell asleep at the beach, and the answer is it got second-degree burns. I thought that was funny because if you all remember, quadratics, the parent function for a quadratic is y equals x squared. This is what a quadratic is. And we're talking about degrees of polynomials. We're talking about the highest exponent in quadratics. The highest exponent is the x squared, and it's the 2. So this is a second-degree polynomial. So that's why they're saying it got second-degree burns from being out in the sun and getting toasted by the ultraviolet radiation. So before I get into the actual practice problems, I would really appreciate it if you all could hit the like button, hit the subscribe button, and hit the post notification bell. Please also comment your thoughts and share using all our socials, which you can find in the description box. All right, let's get rolling right away with this first practice problem. We're going to be classifying polynomials, and I'll show you exactly how. So the problem itself is we're given this polynomial. We're asked to write it in standard form, meaning we have to write it in descending order from the highest degree, the term with the highest degree, to the term with the lowest degree. We want to simplify it and then write it in standard form, and then we want to classify it by the degree, meaning the term with the highest exponent, and then the number of terms that are going to be in the polynomial. Remember, terms are separated by addition or subtraction. Here's going to be the solution pre-written for you, so if you want to pause and copy it down, go ahead, but I'm going to move on and I'm going to be rewriting this with you and explaining the steps as I go. All right, so the first thing we want to do is we want to look at the polynomial we're even given. It's 5 plus 7x minus 6x to the 5th plus 3x to the 4th minus 5. And as you can see, this just is not simplified. It's not written in proper standard form in descending order, and we also have to combine like terms. So the first thing I'm going to do is I'm going to rewrite this polynomial 5 plus 7x minus 6x to the 5th plus 3x to the 4th minus 5. You can easily see that the 5 at the front and the 5 at the end cancel out because this is a positive 5 and this is a negative 5. 5 minus 5 is equal to 0. And I just threw that in as a trick to hope you noticed it. So I'm just going to cross those out. So those cancel out with each other. And let's rewrite what we have left. So the 5s are gone. So now we just have the 7x minus 6x to the 5th plus 3x to the 4th. Okay, we can't combine like terms here because each of these terms, the x's are raised to a different exponent. Here it's raised to 1, here to 5, here to 4. We just cannot combine them because they're not like terms. So let's rearrange them in proper polynomial standard form in descending order. So we want to put the term with the highest exponent first. 7x is one term, negative 6x to the 5th is another term, and then 3x to the 4th is the third term. As you can see, negative 6x to the 5th has the highest exponent, so we're going to put it first. Negative 6x to the 5th, and then that's out of the way. How about this? 3x to the 4th has a higher degree than 7x, so we're going to write plus 3x to the 4th, and then we'll add this plus 7x to the end. So this is our polynomial in proper standard form. Now we got to classify it by degree and number of terms. Remember, whenever we classify a polynomial by its degree, we're looking at the leading coefficient, we're looking at the leading term, which is this one. The leading term is the one in the front, because this term is the one with the highest exponent. It's always going to be the one with the highest exponent if you'd put this in proper polynomial standard form. In this case, it's negative 6x to the fifth. So we're going to look at negative 6x to the fifth's exponent, and that is 5. And that's what we're going to classify this whole polynomial as. Remember, when we say to the fifth power, it's going to be a quintic polynomial. But then we also have to classify it by the number of terms. Well, terms are separated by addition or subtraction. Like we said, one of them is negative 6x to the fifth, the second one is 3x to the fourth, and the third one is 7x. So there are 3 terms, and if there are 3 terms, it means tri. So it's a trinomial. Tri means 3. So we would classify this as a quintic trinomial, and that would be your answer. All right, so that one's out of the way, kind of easy. It's supposed to be somewhat of a warm-up classifying polynomials. Let's look at this next one. In this one, we're going to be determining end behavior. We're not going to be graphing in this one, but we're just going to be looking at the equation of a polynomial, and just by using the equation, we're going to determine end behavior. If you remember the table from the last lesson where we talked about how when we looked at the leading coefficient, ax to the power of n, and we talked about the relationship. When a is positive and n is even, the end behavior should be like this. When a is negative, n is positive, n is even, then behavior should be like this. And we just went through all those scenarios in that table. There are 4 scenarios, and we'll be applying that table. Remember how I said to memorize it? Well, we're going to be applying that to solve this problem. So the problem is determine the end behavior of the polynomial function. The one we're given is y equals 2x to the fourth minus 1 plus 19x to the ninth. Here's your solution pre-written if you want to copy it down. Take a second to pause and do that if you'd like. Okay, now I'm going to run through that exact same problem with you. So the first thing I want to do is I'm just going to rewrite the polynomial we were given. Y equals 2x to the fourth minus 1 plus 19x to the ninth. The first thing I want to do is I want to write this in proper polynomial standard form, so in descending order. As we can see, there are 3 terms. We got the 2x to the fourth, the negative 1, and the 19x to the ninth. The 19x to the ninth is raised to the power of 9. And that is the highest degree out of all of these 3 terms. So I'm going to put the 19x to the ninth in the front, 19x to the ninth, because we want to remember to apply the rules we learned about end behavior. We need to know what the leading term is. In this case, leading term needs to be what we derive using the proper standard form. In this case, it looks like the leading term is 2x to the fourth, but this isn't in proper standard form. So we need to put it in standard form to be able to figure out what the real leading term is. And then what comes after that, you can easily see it's 2x to the fourth plus 2x to the fourth. And then we're going to add that minus 1, which is a constant at the end. The constants will always go last. All right, so remember how we talked about that table like I was referencing from the last video? Well, the leading term is going to be generally what we call ax to the power of n. A is going to be your leading coefficient. So in this case, if our leading term is going to be 19x to the ninth, 19x to the ninth, a is going to be your leading coefficient, which is 9. X is just going to be your variable, which is going to change based on what you plug into the function. And then n is going to be your variable, or the degree of the polynomial. So what we want to do is we want to look at what a is. We want to look at what n is. And when I say we want to look at what a and n is, this is what we're trying to focus on. When you look at a, we're trying to determine what the sign is of a. Is it positive or is it negative? That's what we want to figure out. And we can look at a, which is our leading coefficient. Well, 19 is a positive number, so a is positive. Then we want to look at n, which is the exponent to which x is raised to in the leading term. In this case, the exponent is 9, which is an odd number. So when we look at a, which is the leading term, we want to see if it's positive or negative. That's it. When we look at n, which is the exponent, we want to determine if it's odd or even. In this case, it's 9, which is odd. If we remember that table from last lesson, when n is even and a is positive, the graph will be up and up. When n is even and a is negative, the graph will be down and down. When n is odd and a is positive, the graph is going to be down and up. And when n is odd and a is negative, the graph is going to be up and down. You're just going to have to memorize that. So in this case, like I said, the graph is going to be down and up. So that is the end behavior, and this is going to be your final answer. All right, let's go to the next problem. So problem number 3, we're going to be looking at coefficient and degree. This is a bit of a challenging problem. I actually pulled this from one of the practices I had to do when I was in Algebra 2, and this was put towards the end of that practice worksheet because it is a more difficult problem, but I thought it was very important to include because this Algebra 2 course, I try to make it as difficult as possible. And when I say difficult, I mean challenging, but I promise to work you through everything so you understand it. So here's the problem. So I want you to determine the sign of the leading coefficient and the least possible degree of the following polynomial function. So here's the graph. So this is what you're going to be given. And what I'm asking you to do is look at this graph, and I want you to determine the sign of the leading coefficient. So remember from the last problem, ax to the power n is going to be our leading term. Well, we're trying to determine what the sign of a is, and then we want to determine the least possible degree of the polynomial function. Remember, the leading term is the term that has the greatest degree of all of the terms in the polynomial function. That's why we put it first. So we're trying to determine what the smallest degree of that polynomial function is going to be, and I'll explain exactly how you figure that out. So here's the solution already pre-written for you. I went in as much detail as I could because I remember when we did this in class, we didn't put down this much information. It was kind of like we reason it out. It's a very logical reason. It's a very logic-based question. You have to think it out rather than doing the actual math behind it. You have to apply properties of polynomials. But I wrote everything out, my whole thought process for you so that you understand exactly how I got to the final answer. And I'll be running through that with you again now. Okay, so the first thing I did was I literally just sketched this graph over again. And the thing is, if you remember from quadratics, this looks a lot like a parabola. And I just want you to keep that in mind. So the next thing we want to do is we're trying to determine what A is. So A, whoops, sorry about that. So A is going to be remember our leading term is what we're focusing on here. So the leading term, and remember, we don't know what the exact equation for this polynomial is. All we've been given is this graph, and we're trying to figure it out. We're not trying to figure out exact values, but we're just trying to derive as much as we can from the properties of this graph, especially the n behavior. So the leading term is ax to the power of n. We're trying to figure out what the sign of the leading coefficient is. Remember, the leading coefficient is going to be a. So we're trying to find out, is a positive or is a negative? Well, if we look at this, it looks a lot like a parabola, right? And when we talked about in the quadratics unit, when a parabola is shaped like this, remember how I said it's like a bowl? That means it is positive. The leading coefficient is positive. However, if it was shaped like this, we can look at this as being upside down. It's negative. So this is the difference. So what we're looking at is something that opens upward, not downward. Since it opens upward, it's not reflected, so it's positive. So we can say that A is positive. So I hope you realize how we're incorporating things we learned from previous units. So A is positive, and my reasoning is because this graph opens up. Notice how I don't want to call this a parabola, but it is shaped like one. So that's why I'm applying the same properties of parabolas to this graph, but I'm not calling it a parabola. Next, we can look at the n behavior. Well, this part of the graph goes up, and this part of the graph also goes up. So this graph exhibits up and behavior. Both of the ends are going the same way, up and up. If it's up and up, that means A definitely, if you remember that same little chart I was talking about, and I was talking about in the last problem, when the graph is up and up and A is positive, it can also reveal to us that n is even, like we talked about. So we know A is positive and n is even. All right, so if n is even, what does that mean? Well, we know A is positive, so we determine the leading coefficient. It's going to be positive. However, we didn't determine the least possible degree of the polynomial function, so we didn't determine what n is going to be equal to. Well, we know n is even, but we need to give it like an actual numerical value. And you might be thinking, well, if n is even, it could be 2, meaning this could be a quadratic. Because remember, y equals x squared is going to give you a quadratic that looks something like that. Sorry for my terrible parabola. However, I do want you to take into account that right here, right near the vertex, the graph kind of flattens. It's not a perfect parabola, and I want you to keep that in mind, and it's done on purpose. It's supposed to trick you and make you think that you're working with a parabola, which is a second-degree polynomial for quadratic. However, because it flattens right here, it's not a perfect parabola, so you cannot assume that. Therefore, what I like to think of is if it doesn't perfectly resemble a parabola, which is a second degree polynomial, which is the lowest even degree of a polynomial, you bump it up to the next even one. So this would actually be a quartic, and that's the right answer. So it would be a quartic polynomial. And for those of you who aren't sure what quartic means, it is just fourth. And the reason, again, why I say this is because this is not a quadratic, and I'm just including this note at the bottom. Not a quadratic because the graph flattens, like I tried to show you to the right, because graph flattens. And even small things like that can indicate to you that this is not a quadratic you're working with, it is actually a quartic. So like I said before, if you see something that does not look exactly like, for example, if we saw a graph and we thought it was a linear graph, but it wasn't perfectly aligned, then we can bump it up to the next odd polynomial possible degree, which would be cubic. And you would keep going until you found something that matched. And this is a graph of a quartic. So that's how you would determine this one. It's a bit of a tricky problem, but I hope you were able to stick in there. Okay, so problem number 4, a cubic function. So in this unit, even though we're working with polynomials with degrees greater than 2, greater than quadratics, we're going to focus so much of our attention on cubics. So that's why I want to do a problem focused solely on a cubic. So here's the problem. Graph the cubic function and describe end behavior, turning points, and increasing and decreasing intervals. So there are 4 things we need to do with the cubic function y equals 3x minus x cubed. We need to graph it by hand, and then on the next slide, I'll show you how to do it with the TI calculator. So first, we're going to graph it by hand, and then we're going to describe the end behavior. Is it up and up? Is it down and down? Is it up and down? Is it down and up? That kind of thing. We're going to indicate where the turning points are. Remember, a turning point is when a graph switches from increasing to decreasing or decreasing to increasing. And then we're going to be indicating where exactly does the graph of this cubic function increase and across what interval does it decrease. So that's what we're going to be doing. And we're going to be bringing interval notation, which was one of the first lessons I did in this course, into play in this problem. So here's the solution. Here's it graphed by hand. I already did this for you. And here's how I answered the questions that were inside of this one question, the 4 different components we were asked for, and all my work to get to the answer. So I'm going to go through that again with you exactly. So here is a plain graph for us to start from scratch. Okay, the first thing I want to do is I want to look at what we're working with. Here's the cubic. It's not in perfect polynomial standard form. If it was, it would be y equals negative x cubed plus 3x, because remember, we have to put it in descending order, and this term right here goes to a power of 1, this term it goes to a power of 3, yada yada. But we don't need to worry about that because we're not asked about that. We're just asked about the properties of this equation. If putting it in standard form works for you, go ahead, but at the end of the day, it doesn't really matter. It might actually end up wasting your time when you're taking an assessment. So the first thing I want to do is I want to graph it. But how exactly am I going to graph it? Well, we're going to incorporate the same skills that we did with quadratics. We're going to make an XY table, which can always come in handy. We're going to plug in X values, and then we're going to plug X values into this polynomial that we've been given to get the Y values. So for X, I'm just going to plug in these following 5 points: -2, -1, 0, 1, and 2, because they're all centered around the origin. Pretty easy to work with, because this is going to be a very simple graph compared to some other cubic functions you might have to graph later on, and that we'll be graphing later on in this unit. So let's first plug in -2. 3 times -2 is -6, and then you have -2 cubed. -2 cubed is -8. -6 plus -8 times -1 with the negative sign is going to give you -6 plus 8, which is going to give you 2. If you plug in -1, maybe I should start from here. -1 cubed is -1. -1 times the negative sign is +1. 3 times -1 is -3. -3, -3 minus 1 is equal to -4. Sorry, I'm trying to do all this. Sorry, no. -3 plus 1 is equal to -2. My bad. Okay, next we're going to plug in 0. 0 cubed is just 0, pretty simple. And then 3 times 0 is 0. 0 minus 0 is 0. Plug in 1. 1 cubed is just 1. 3 times 1 is 1. 3 minus 1 is 2. And then lastly, 2 cubed is 8, 3 times 2 is 6, 6 minus 8 is going to give you negative 2. So you just simply plug your x values in, and then you get your y values. So these are going to be the 5 coordinates that we're going to be plotting on this plane. So the first one is negative 2, 2. So I'm going to find negative, go left 2, and then up 2. That's my first point. Then for negative 1, negative 2, go left 1, and then down 2. Negative 1, negative 2, 0, 0, simply the origin. I'm going to plot that here. 1, 2 is our next point. 1, go up 2. And then the next point, whoops, sorry about that menu. Then the next point is going to be 2, negative 2. So go right 2 and then down 2. And here is what looks kind of, whoops, that point disappeared. I don't know why. Okay, so that's going to be kind of funky looking, but luckily for us, we know how a cubic looks. So we're going to connect the dots. Cubic will kind of go like this. Kind of wacky looking, I know. And then you're just going to follow it down like that. Go up like that. Okay, so this is how we're going to, I'm sorry, I know it looks very, very messy, but this is how it looks. It's perfect. So the end behavior, we're going to be able to observe the end behavior first. And as you can see from this, the end behavior, we read it left to right like a book. So it starts up and then it goes down. So the end behavior is going to be up and down. For cubics, the end behavior is always going to be one and the other. So you're going to always have an up and you're always going to have a down. But it might change depending on your A term. In this case, our A was negative. So that's why our A was negative, and then our highest degree was odd. So that's why it goes up and down. So that's where you incorporate that table as well, so that you know exactly how you're going to draw your graph. So that's why our end behavior is going to be up and down. Then we got to look at turning points. Oops, sorry about that menu keep coming up. Okay, so next we're going to look at our turning points. Remember, our turning points are where the function goes from increasing to decreasing, suddenly changes, or if it goes from decreasing to increasing. And the two turning points should be pretty obvious. When we start coming down from negative infinity and we start approaching 0, we see that the function keeps decreasing until it hits this point, and then suddenly it starts increasing. So this right here is going to be a turning point, and it's going to keep increasing until it reaches this point, and then it's going to continue decreasing for negative infinity. So here is another turning point. Turning point right here, we can easily name it as the point negative 1, negative 2. So negative 1, negative 2 is one of the turning points, and then the other turning point is going to be the one that we labeled here. It's going to simply be 1, 2. Yeah, so let me write that down. All right, so now let's identify the intervals across which this function decreases, and we're going to be using interval notation. So the first interval we talked about, the function is decreasing until it reaches this turning point, negative 1, negative 2. So it's decreasing from negative infinity. Remember, this arrow is just going up, 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 just towards negative infinity as the domain progresses towards negative infinity. So we're going to be decreasing from negative infinity all the way to this turning point. And the turning point, the x value of the turning point is negative 1. And remember, we write these intervals in regard to the domain, so the x value. It's also decreasing from this turning point here all the way to positive infinity in regards to the domain. So the turning point right here is starting at the x value of so this interval is starting at the x value of this turning point, and the x value of this turning point is 1, and it's continuing towards infinity. This function will just continuously decrease. There's only one part of this function that's going to be increasing, and let's see if you can get the interval while I'm writing increasing from. Okay, so hopefully you had a second to look at the graph. It's increasing this right along this interval right here. So it's increasing when it starts to increase when x is equal to negative 1, and it stops increasing when x is equal to 1. So the interval would be negative 1 to 1. Across this small interval right here is when the function is increasing. And that's it. We pretty much addressed everything that was asked in this problem. Okay, everyone, I'm going to be quickly showing you how we did the last problem, but I'm going to do it on the TI calculator. The first thing you want to do is take this cubic function we've been given, y equals 3x minus x cubed, and go to your y equals button to graph it. Next, you just want to type it in, 3x minus x cubed. Doesn't need to be in standard polynomial form. This is perfectly fine. It'll still graph it for you. Then you want to hit the graph button, which is right here, and give it a second to load. And as you can see, you can observe the up and down behavior that we saw if you read it left to right, which is exactly the same as the answer we got in the last problem. Then we want to find the turning points. To find the turning points, which we know to be -1, 2, and 1, 2, we want to hit the it's -1, -2. It's written as -1, 2, but it's -1, -2, and 1, 2 by hitting the second calc, then minimum or maximum. I'll show you what I mean. So second, then we hit the trace button with calc above it, and let's first hit minimum. So if I hit 3, I'll get minimum, and you'll see that it's flashing here. It's similar to how we found the vertex of a parabola. So first it says left bound. I'm going to scroll over to the left side of this turning point, which we know is down here, hit enter once. Then I'm going to scroll over to the other side, which says right bound, hit enter again. And then I'm going to guess where I think the turning point is, which is right here. I'm going to hit enter one last time, and I'm given the coordinate -0.99999, etc., -2. And I can round this up to -1, so our turning point will be -1, -2. I say minimum because in this area, this is like the minimum point, so of this cubic here. So that's why I do minimum. We're going to do the opposite to find this turning point, which is like a maximum because it's all the way up here. I'm going to hit second, trace, and then I'm going to hit 4 for maximum. It's asking left bound first, so I'm going to go to the left of that turning point, hit enter, go to the right of that turning point, hit enter, and then I'm going to guess where the turning point is, hit enter, and then the calculator will give me its guess, 1.000012, and we can round that up to the turning point 1, 2. And now you can easily determine where the increasing and decreasing intervals are. You can see the function decreases from -infinity all the way to -1, and then it increases, and then it starts decreasing again from 1 to infinity. The only place it's increasing is from this small interval of -1 to 1, and that's how you do it on the TI calculator. All right, so let's move on to our next problem. In this problem, number 5, we're going to be looking at a table. So here is going to be the problem up here. So the problem is find the degree of the polynomial function using the data shown in the table. And I actually hinted at this in the last video where we're going to be given a table, and then using the table, we're going to have to compare y values across x values and then determine what the degree of the polynomial is. So for example, we have to be able to tell, is this a quadratic, is this a cubic, quartic, quintic, what are we working with? We won't have to say exactly what the equation for the polynomial is, but we'll have to determine what the degree is, which is being asked in this problem. So here is the table we've been given. The x values are -2, -1, 0, 1, 2, and the corresponding y values are -15, -9, -9, -9, and -3. Here is the solution pre-written for you if you just want to look at it or copy it down, but I'll be going through the exact same thing with you. Okay, so let's do that now. So the first thing we're going to do is we're going to look at the y values, and the y values are what we're going to be focusing on. So what we're going to do is we're going to compare the y values. So we're going to see the difference between this y value here and this y value here. So what is the difference between -15 and -9? Well, I'm adding 6, so that is the difference. So I'm going to put +6. What's the difference between -9 and -9? Well, there's no difference at all, so I'm just going to put +0. We didn't add anything, we didn't subtract anything. What's the difference between -9 and -9? Again, we didn't do anything, so I'm going to do +0. And what's the difference between -9 and -3? Well, we added 6 again, so I'm going to put +6. Then what we do is we look at what we have here, this +6, +0, +0, +0, and we do the exact same thing we did, but between these numbers here. So what's the difference between 6 and 0? Well, you subtracted 6 to get from 6 to 0. What about 0 and 0? Well, you didn't do anything. So I'm just going to say +0. You didn't change any value, you didn't add or subtract anything. And how about 0 to 6? Well, you added 6 to get from 0 to 6. And then we do that again. So to get from -6 to 0, well, I added 6. And then to get from 0 to 6, +6, we added 6. And notice we keep doing this until the numbers we're either adding or subtracting are exactly the same. So here we've gotten them to both be +6, so adding 6. So we stop here. So how do we determine what the degree of this polynomial is? Well, we look at how many kind of layers we had to go through. So this was like our first layer, this was our second layer, and this is our third layer. So you can think of it like layers. That's how I think of it. If we stopped here, it would have been a quadratic. If we stopped here, it would have been linear. But we stopped at a third level, so this is going to be a cubic polynomial. And that answers the question, what is the degree of the polynomial whose data is shown in the table? So third. And that would be the answer to this problem. All right, so let's move on to the final problem, which is a challenge problem. If you want to stick with me through this, I highly, highly encourage it because it was on my homework. We were expected to know how to do this problem. So I would highly suggest you stick with me, but it is optional. So if you want to skip to the end of this video, I'll see you there. Okay, so for those of you who stuck with me, let's do this problem together. It's going to be kind of hefty. Here's the problem. A cubic polynomial function called f has a leading coefficient of 2 and a constant term of 7. If f of 1 equals 7 and f of 2 equals 9, find f of negative 2. So first we got to find out what this cubic polynomial is, and then we got to plug negative 2 into it to find out what the value would be when the function is f of negative 2. So here's the solution pre-written. I know a lot of work, but we're going to get through it. If you want to pause and copy that down, you're free to do so. Okay, so let's run through that problem again. I'm going to take the information we've been given and write it in terms of the givens, what we've been given. So the function is f of x, we've already been told. And we're going to assume that it's in perfect polynomial standard form. Since it's a cubic, it's going to have a cubic term in the front. Then it's going to be followed by a quadratic, then a linear, then a constant. So that's what we're going to write it as. We know that the leading coefficient is 2. So it's going to be 2x cubed because, again, this is a cubic polynomial. Then it's going to be followed by a quadratic. However, we don't know what the coefficient of the quadratic is, so I'm going to give it a variable b. So bx squared. We also have a linear term that comes after that, but again, we don't know the coefficient of the linear term, so we're going to call that cx. And lastly, we have a constant which we've been given, which is 7. So we're going to add plus 7 at the end. Now we're going to be looking at what we've been given. When f is equal to 1, meaning we plug 1 into this, we're given 7. And when we plug 2 into this function, we're given 9. So what are we going to do? We are going to plug these values in for x. So let's do that down here. I'm going to rewrite this as, because when the function is equal, when you plug 1 in for x, the function is equal to 7. That means we can replace f of x with 7. So 7 is equal to 2 times, we're going to plug 1 in for x, so 2 times 1 cubed plus b, because we don't know what b is, times 1 squared, plus c, because we don't know what c is, times 1, plus 7. We're going to get 7 is equal to 2 times 1 cubed is 1, plus b times 1 squared is 1, plus c, because c times 1 is c, plus 7. And then we're going to get 7 is equal to 2 plus b plus c plus 7. Now we want to subtract the 7 from both sides just to get rid of it, because we can do that to simplify it. So we get 0. So 7 minus 7 is equal to 0. 0 equals 2 plus b plus c. And let's try to get these variables on one side by themselves. So we're going to subtract the 2 from both sides and get negative 2 equals b plus c. We're going to repeat this exact same process, but using the information that f of 2 equals 9. Because f of 2 equals 9, we're going to replace this f of x with 9, because that's the value of the function when x is equal to 2. So 9 is equal to 2 times, well, now we're going to plug 2 in for x. 2 times 2 cubed plus, we don't know what b is again, b times 2 squared plus c times 2 plus 7. We're going to do the exact same thing we just did. So 9 is equal to, well, 2 times 2 cubed is 2 times 8, plus b times 2 squared is b times 4, plus 2c plus 7. And we're going to continue simplifying. 9 is equal to, well, 2 times 8 is 16, plus b times 4 is 4b, plus 2c plus 7. Now let's subtract 7 from both sides. 9 minus 7 is 2. 2 is equal to 16 plus 4b plus 2c. And we can subtract 16 from both sides. 2 minus 16 is negative 14, which is equal to 4b plus 2c. Again, we're trying to isolate the b and c variables. Okay, so the next thing we're going to do is we are going to use elimination method. So we've gotten it down to just the b and c variables. So we're trying to figure out what they are. So we're going to use elimination. Remember our systems of equations, when we don't know two variables, we can use substitution, elimination, or graphing to find out what the variables are. So what we're going to do is we are going to rewrite them and in terms of the elimination method. So negative 2 equals b plus c. And we are going to actually multiply this times 2. so that we can get this to become negative 4. Sorry, we're going to multiply this times, I'm just checking my work. We're actually going to multiply this times negative 2. So my bad, I actually put 2. We're going to multiply this times negative 2 so that we can get 4 is equal to negative 2b minus 2c. The reason we do this is because we're going to add it to negative 14 is equal to 4b plus 2c. And if you see, the reason I multiplied it times negative 2 is so that we can cancel out the 2's. So now we have a negative 2c, which cancels out with a 2c. And now we'll get 4 plus negative 14, which is equal to negative 10, equals negative 2b plus 4b, which is equal to 2b. And if we divide both sides by 2, we get b is equal to negative 5. Now that we know that b is equal to negative 5, we can literally just plug it in to an equation like 4 is equal to negative 2b minus 2c. So if I plug b in for that, we get 4 is equal to negative 2 times negative 5 minus 2c. We get, if we multiply negative 2 times negative 5, that is 10. 4 minus 10 is negative 6. And then if we divide both sides by negative 2, we get c is equal to 3. Okay, but we haven't answered the final question yet. They're asking us to find what f of negative 2 is. So now that we know what our actual polynomial is f of x is equal to 2x cubed, b is negative 5x squared, c is plus 3x plus 7. We're going to plug 2 in for x to finish this problem off. So f of negative 2, let me put it in this corner right here, f of negative 2 is equal to 2 times negative 2 cubed minus 5 times negative 2 squared plus 3 times negative 2 plus 7. This is going to be equal to 2 times negative 2 cubed is negative 8 minus 5, negative 2 squared is 4 minus 6, because 3 times negative 2 is 6, plus negative 6 plus 7. Continue to simplify this. 2 times negative 8 is negative 16. Negative 5 times 4 is equal to negative 20. Carry the negative 6 plus 7 down. And if you simplify this, negative 6 minus negative 20 is negative 36. Negative 36 minus 6 is equal to negative 42. Plus 7 is going to give you negative 35. So that is going to be your answer. That is the value of the function when x is equal to negative 2. So that's how we solve that. The challenge problem, I understand if it was a bit difficult, but good job for sticking through it. So thank you for watching this video. I really appreciate it. If you enjoyed, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials, Pinterest, Facebook, Instagram, Twitter, and we will get our TikTok up and running. Also, visit our website and email us if you have any inquiries at all. See you in the next Algebra 2 lesson.